Okay, so let's start our lecture today. So, okay, so oh, yeah. Okay, so yeah, I think last time we are left to prove part E. Okay, so yeah, so let me rewrite the statement. So each element phi is deck gamma take away identity has no fixed points. In fact, if U is an evenly covered domain X, domain X and U dot is a component of U tilde, which is gamma inverse U, gamma inverse U. So then the set U1, which is being defined as phi of U0, is a component of U tilde that is distinct, hence different from U0. That is distinct hence disjoint from U0. Okay, so let me just do the proof here. Okay, so I want to show that each element phi in this deck transformation group of this gamma take away identity has no fixed point. So okay, so why it has no fixed point? So so if you take any element, okay, so so let's have what happens if phi x, oh So if you have phi x equal to x, yeah, I think we have resolved by last time, right? Because saying that if you have a gamma, if you have a path, then if you have the path that is the initial point is so what is the initial point? Yeah, I remember last time we have these two paths, right? So the thing is that I think if you have okay, so I think what you have is that if you have a phi tilde of this okay, so I think okay, so this is like alpha, right? So I think from last time, so this is like alpha tilde 1, and then this is like x naught x naught tilde, and then so gamma is a path from x naught tilde to this x, right? So suppose this is x. Okay, so this is like gamma tilde, and then I think this is like small gamma tilde 1, right? Small gamma 1 tilde. So so then what we have okay, I think what we have is that we have I think remember we have this one, right? Okay, so we have this one as a okay, so if you plug in so what do you plug in? So you plug in gamma. Oh, okay. Because do we have this one is equal to Yeah, I think we do have that, right? So, because we know that this, okay, because we know that this chi of this phi tilde is equal to this alpha, right? So therefore, this is equal to same element gamma of this alpha tilde not, where this alpha tilde of let me think. Okay, yeah. So we show that this alpha tilde is actually the alpha tilde that's being denoted here. So remember, this alpha tilde is a unique lifting of this alpha to the space of with alpha tilde 0 equal to x 0 tilde. Yeah. Yeah, so this is a unique lifting of alpha. So okay. So okay, so then we also know that this alpha tilde here is a lifting of this alpha, right? So therefore, yeah, so therefore this one, and then we know that, okay, yeah, yeah, so okay, and then by the yeah, by the definition that the image of this phi tilde under this characteristic map chi, so under this chi is equal to this alpha. We know that this alpha tilde it's a lift of this alpha, and then this alpha tilde of 0 equal to x naught and alpha tilde of 1 is equal to phi of x naught tilde. Yeah, sorry, phi tilde of x naught tilde, and then yeah, we also know that this since this by the unique lifting property, we know this alpha tilde to be the lift of alpha tilde path in x tilde with alpha 0 equal to x naught tilde. Okay, so this is actually the same class like I showed last time, or wait, did I show last time they're the same, or I think I used some like a homotopy property, right? But actually I think they should be the same because of the unique lifting, yeah, because wait. No, they are not the same. Okay. They are not the same because but they share the same endpoint because this is not like the same number. They share the whole yeah, sorry. Yeah. So they are not exactly the same, but since they are equal, so they are homotopy to each other. So yeah, I think last time I showed that these two are that they are same point. Okay. And then yeah. So then you have okay, so what do we have here? So I think last time I showed that, so this is like yeah. So this is 1, right? Yeah, I think last time I showed that this phi of this x is equal to this gamma tilde of 1. Okay. Okay, what does that mean in general? Okay, so that means, yeah, so that means, wait, did I show last time? Okay, yes, I showed it last time. Okay, good. Yeah, so that means, I think this means that, because of the unique lifting, right? Because both these yeah. So basically the way I show that is because remember this so this is a lifting, right? So this gamma composes this, yeah. So basically, yeah. So since this one is by definition is equal to gamma, right? And then this one, which is same thing as that, is also a lifting. So yeah. So this one, the phi tilde of gamma tilde by definition is also a lifting of this gamma. So and of course, and then we know that the inner point is equal to this alpha tilde 1 because yeah, we show it here, okay. And then what we have next? And then okay, so therefore wait, what is gamma 1 by the way? How will you define gamma 1? Oh, gamma 1 is a unique lifting. Okay, so gamma 1 is a unique lifting of this alpha of this gamma with each point. Yeah, so this one is also a lifting. Yeah, we show that this one is also a lifting. So this gamma 1 is a unique lifting of this I think this gamma, right? Because yeah, at first we define like a curve gamma from here to here, I think. Yeah, so gamma is the path from x tilde to x. Yeah, sorry, gamma tilde. Yeah. Okay. And then you define like gamma to be, yeah. So first you start with this, if you fix upon x, you let this gamma tilde be a path from this x tilde to x, and then you do like the gamma to be the projection of this gamma tilde, and then you do a lifting of this gamma to here, and then you say that okay, so why do that, right? Why do the gamma compose with this? Sorry, why just do that? So this is also a lifting because of this property. But they share things that share the same at starting point, right? Yeah, so same initial point. So then these two must be the same. So yeah, so this concludes this result. Okay, so because they are the same, right? Because of the unique yeah, because of the unique lifting property, yeah. So then what you have is that so if this, okay, so let's see, if this phi of x, so let's say that I think this argument is this x naught is arbitrary, right? Yeah, so this is x naught arbitrary. So yeah, so if we say because this is arbitrary, so why don't we just take to be that, okay? So then you will have, so this implies what? So you may have like, so any path is being fixed, okay? Oh, okay. Okay, I think that just shows the result, right? Because if you take, because this x is also arbitrary, right? And then this gamma is also arbitrary. So basically, the idea is that if you fix x0 to x0, then this implies that phi of this gamma tilde has to be the same, because the same argument applies here, same argument. Okay, therefore by the unique lifting, by the unique lifting property, so therefore this two must be the same curve. Because it must be the same curve. So this implies that this implies that if you have any point, right, other than x, because I think this space is do we have the past connectedness? Oh, okay. You see, like, okay, this x tilde is actually a universal covering. Okay, because it's a universal covering, we can take any path, right? So any path is being fixed. So therefore, we show that so basically the idea is that you imagine this you imagine. So basically, you think of these 2 points are the same, right? Because this alpha 1 is like phi tilde of x, tilde, sorry. And then these two are the same, so therefore, these two must be the same, right? So because it's phi of this gamma tilde and this one, we show that these two are the same. But if the unit point are the same, then this gamma tilde and then this gamma 1 tilde are actually the same point. So basically, same line, and then we show that this one is exactly the same as the phi tilde of, so namely we'll have, like, for any point, if the phi, if I connect the point with this point, integral point, and then if I apply phi to it, wait, what I want to say? So if I apply phi to it, then because it's because it has to be the same point. It has to be the same line. Okay. I think that shows the result, right? Because because it fixes this point, right? This actually arbitrary. You take a path. You fix the path. Then therefore, so therefore it should be therefore it fixed out the birth point. Okay, I think that's the proof. All right, so let me see. So basically, okay. Anyway, let me continue. Let me continue. So sorry, I haven't finished yet. So in fact, if U is an evenly covered domain in X, and then U0 is a component of of U tilde, which is gamma inverse of U, then the set U1, which is the same thing as phi of U0, is a component of U tilde that is distinct. So maybe let me draw some pictures here. So evenly covered domain X. So here you have so let's see, this is X, I take the evenly covered set, so this is like U tilde here, and then so U0 is a component of, okay. I think what the author means here is that this is like U tilde, okay, and then it's a component of this one, then the set U1, which is phi of, oh, okay. It's a component of U tilde that is distinct. Oh, okay. I see. Okay. Distract from U0. Okay. Ah. Okay. Okay, I think can somehow manipulate this argument, right? So, okay. So the idea is that I think if you take any point, let's say x naught, x naught tilde, okay, to be inside this U naught, then this is like x naught here, and then what you do is that you take any wait. Yeah, because this is wait, this is connected, right? Wait. You may call domain X, and then set U1. Okay, so suppose that because this phi is okay, because this phi is non-identity, right? And we show that it has no fixed point. So therefore, yeah, therefore we have that. Let's suppose that this is like the set U1, okay, where it contains the image of this phi of x naught tilde, which is this point. Okay, and then yeah, so it's a little bit yeah, okay, and then we want to show that. Namely, we want to show that this U1 and U0 they can be identified by the phi of U0 equal to U1. So what happens? So if you take, can you take any path? I don't think you can, because this set is only like I think, yeah, maybe you can, but I feel like there are some issues here, because let's say that if you take this point here and then you do a connection, and then yeah, so cover domain. Wait. It's an even, okay, it's an evenly covered domain. In X. If you take any path, okay, so if you take any path from here to here, so it may not intersect. It's U0, okay. Okay, what, okay. Because this gamma is, yeah, because this gamma is, wait. Yeah, so the issue is that this, yeah, let me think. Universal covering. Wait. Locally path connected. Okay, I think I can start here. So, okay, so, okay, maybe I'll come back to it later. Okay, yeah, sorry. Okay, so, okay, okay, connected. Okay, anyway, sorry. Okay, so yeah, let me state the next. So. Okay, so let's see for the definition. Okay. Okay, so now we let this gamma be a subgroup of the group of self-homomorphism of a locally compact Hotto space X. Subgroup of the group of self-homomorphism of a locally compact Hotto space X. Hotto space X. Okay, so then we have A. I think locally compact means locally you have a for any open set you have a compact set contain the open set. But let me check. Okay. Okay. So yeah. So locally compact means that each point has a neighborhood that lies in a compact set. Okay. Okay. Oh, or like okay. If every point P X and every neighborhood U of P, there is a relatively compact neighborhood V of P U. Okay. Relatively compact neighborhood V of P U. Okay. All right. So yeah. So let's continue. So here. Let's see. And then, so for part A, we denote by this relation gamma, the equivalent relation on X. Given by, so X is related something gamma to Y, equivalent of saying that small gamma X equal to Y for some gamma in this gamma. Okay. And then by so we use the notation this gamma take away X, the quotient space. X quotient by this relation. Okay. Which is given the quotient topology. Okay, and by this gamma of this gamma to be space, the corresponding quotient map. Okay. Okay, so yeah. Okay, so let me erase here. Oh, I think I can write here. So part B. Okay, so the group gamma acts probably discontinuously on X. X probably discontinuity on X. Sorry, probably discontinuously on X. X, if for every compact set K in X, if for every compact set K in X, gamma K intersect K is empty. Gamma K intersect K is equal to empty for all but finally many element gamma of this big gamma. Okay. But finitely many small gamma in the group gamma. Okay. So part C, the group gamma X. Yeah, so this is the definition of probability discontinuity. Okay. The group gamma X freely if the group gamma X freely if for every element gamma in gamma with this gamma is not equal to identity, and every point x in x, we have this gamma of x is not equal to x. Okay. Okay, so let's start with a lemma. Okay. The lemma says let the big gamma be a subgroup of the group of self-homomorphism of a locally compact Hausdorff space X. subgroup of the group of self-homomorphism of the group of self-homomorphisms. The group of self-homomorphisms of a locally compact Hausdorff set X okay, so that is like I forgot again. So so every neighborhood it has a relatively compact, right? So let me see. Yeah, so I also will say X is locally compact if every point Px and every neighborhood U of P, there is a relatively compact neighborhood V of P in U. Okay, so that's the definition of locally compact. Okay, and then okay, so also the X, then is gamma X property discontinuously on X if and only if for each pair of points x, y in X, there exist neighborhoods U of X and V of Y such that gamma U intersect V is empty. For all but finitely many elements gamma of gamma